In this video, we will discuss about the uniform circular motion and more specifically about the centripetal acceleration. And that is, in the uniform circular motion here means that whenever the body is moving in a circular path with a constant speed, then either it's having the constant speed, but still it has the acceleration, which is called as the centripetal acceleration. Now here, more specifically, we will discuss the centripetal acceleration, how it is produced when body is moving with the uniform speed in a circular path. Now let's suppose that car is moving in a uniform circular path. So this one is the circular path. I can draw it like here, and let's suppose this one is the car which is moving in a uniform circular path. So when the car is moving in a uniform circular path, so there are the two important things to discuss about the car. Number one is about speed, and second thing which we need to discuss about it is its acceleration. So when the body is moving in a circular path with the uniform circular path, then its speed is always constant. So when the speed v is the constant, then such a motion is called as uniform circular motion. We call it like the uniform circular motion. So when the body is moving with the constant speed, then it is in the uniform circular motion. Then now what about the acceleration? What will be the acceleration? As we know that acceleration is produced whenever the body changes its speed or either it's changing its direction. Now here in this case, when body is moving in with a uniform circular motion, then it's mean that in that case the speed is the constant. Now the second thing which is changing is its direction. So as I told you that acceleration is produced either by the change in the direction or either by the change in the speed. So here in this case, the body is changing its direction. So at some instant of time, its direction is like this one. At some other instant, its direction is like this one, this one. So it's changing at always at every instant of the time. So the body accelerated due to change in the direction, due to change in the direction of body. So it's not here it's the speed, but rather it is the body direction of the body which causes the acceleration. So again here, if we consider that, let's suppose we have the circular path, that is the circle, and so it has center. So let's suppose that the body, anybody is moving in a circular path with the constant speed. Speed is the uniform or constant speed. So let's suppose it is here at some time, at instant of time, it is at this point. We can call it like the point A, and it has at some other instant of the time. Now it changes its position at some other instant of time. It reaches at some other point. We can call it like the point B. Now this one is the radius vector, this one is also radius vector. I can write it like this will be the delta r and this will be the delta theta angle between two radius vector. Now here the velocity vector, which is always tangent to the path. So the velocity vector when body is at this point, it will be the vi, and some other time it will be the vf. So velocity vector is always tangent to the path and it always perpendicular to the radius vector. So I can say that velocity vector is always perpendicular to the radius of the circle. So it is always perpendicular to the radius of the circle. So here, whenever the body is moving with a constant speed, and but rather it is changing its direction as it is the circular path, so the acceleration which is produced due to the change in direction, acceleration is always points toward the center of the circle, always point towards the center of the circle. So as the acceleration is always point towards the center of the circle, and this, we can call it that this acceleration is called as centripetal acceleration, because it always points towards the center of circle. That's why it is called as centripetal acceleration. So the magnitude of the centripetal acceleration, it can be represented by a c here, the subscript c, which represents the centripetal acceleration, and its magnitude is always equal to v square over r. Here v represents the velocity vector, and r represents the radius vector. So we can derive this relation of centripetal acceleration. So the centripetal acceleration is here the important quantity which we need to calculate for the uniform circular motion in which the speed is constant, but the body is changing its direction, due to which it produces the acceleration, which is centripetal acceleration, and it's having the magnitude equal to v square over r. So it's here you can see that it has the inverse relation with the radius vector. So here we need to calculate this equation, this formula for the centripetal acceleration. Now let's suppose we can derive this relation again by considering the motion in a circular path. So again I can draw a circle, and let's suppose this is the circular path, and this one is the center of the circle. Particle is here at point A, and at some other time it reaches at the point B. As I have told you that the velocity vector is always tangent to the radius, or tangent to the circular paths and perpendicular to the radius. So this one is our radius vector. So I can draw it like this one. If it is at point A, its velocity is vi at some time ti, and at other time, final time tf, I can write it like tf is at it has velocity vector vf. Now I can draw the velocity vector like this one. This one is the vi, and this one is the vf, and this one is the difference in the velocity. And in the same way I can draw the radius vectors like this one. So here this one is the angle theta, I can write it like delta theta, and again this one is the delta theta, this one is the angle delta theta, and this one is the r, this one is r, and this one is difference in the radius vector when body is at point A and when it is the point B. And so this distance will be equal to del r, and this one is the angle delta theta. Okay, now I need to derive the relation AC is equal to v square over r. Now how I can draw, or how I can calculate this relation? And so I can use these three figures. So here you can see that when body is at point A, its velocity is vi, and when it is at point B, its velocity is vf, and time will be the t. I can represent here the time, here will be the tf, and here the time will be ti. So I can write the average acceleration, it will be equal to Vf minus Vi divided by Tf minus Ti, and it will be equal to delta V divided by delta T. Now if you look at both these triangle, and this one is the figure B and this one is the C, both triangle are the same, so I can write the relation between the sides of the triangle. So these are the sides of three sides of this triangle, and these are the three sides of this triangle. So I can write the relation between sides of triangles B and C. So I can write it like, and del V divided by V, it will be equal to delta R divided by R. So from here I can write delta V will be equal to V over R into del R. So this is our equation 1. So now I can write as the acceleration is equal to delta V divided by delta T. So now here I can put the value of delta V. So from equation 1, the value of delta V, these are the equal to V over R into delta R. So I can put this value into this equation. So by putting this value, I will get the centripetal acceleration. It will be equal to V over R into delta R divided by delta T. So this one is our equation 2. This one is the average, I can call it the average acceleration. Now the point A and B, if I can write again here, this one is the point A and this one is the point B. So if point A and B approaches each other's and they become so close together, so at this time the delta V which is like this one, so this one is the Vi, this one is the Vf, and this one is the direction of delta V. And so delta V will point towards the center of the circle. So it means that when A and B approaches so close together, then at that point delta V will point towards the center of the circle. And when it points towards the center of the circle, and then it means that acceleration is also pointing towards the center of the circle, as acceleration is always in the direction of change in the velocity. So if the change in the velocity points towards the center of the circle, the acceleration is also pointing towards the center of the circle. So at the instant when A approaches B, when point A approaches the B, so at the instant when del T will approach the 0, so the time will approach the 0 because both A and B are at the same time, so at same point at the same time. So whenever delta T approaches 0, point A approach point B, so at that instant delta R divided by delta T will approach the speed V. So it will approach speed V. So at that instant we can say that centripetal acceleration, it will be equal to V square over R. When delta R over delta T approaches 0, when delta T approaches 0, delta R over delta T approaches the speed, and in turn the centripetal acceleration will comes out to be v square over r. Now we comes to the dimension of the centripetal acceleration. Now the dimensions of the acceleration. Okay, dimension of centripetal acceleration. Now its dimensions will be as centripetal acceleration is equal to v square over r. So as we know that speed is always measured in the meter per second square, and the units of the distance, r is measured in the unit of distance, and these are meter. So whenever I write the units in terms of dimension, meter has the dimensions of the length, it can be represented by L, and time, second, has the unit of can be represented in the dimension, can be represented by a T. So it's in the square, again the meter, it can be written like L. So the dimensions will be L square over L over T square. So L will be cancelled out, and so AC, it will be equal to L divided by T square. So these are the dimensions of the centripetal acceleration. Centripetal acceleration. So we can say that centripetal acceleration can be measured in the unit of meter per second square. Thanks for watching. For more videos, please subscribe our channel.